Okay, thanks a lot, Andrew, and thanks so much to the organizers, Norbert, and everybody else for having me. It's a really great audience to be able to present this work to, because a lot of you, came up with some of this stuff or could really appreciate a lot of it. I would say basically at the outset, this work is really just sort of taking some other really pioneering work that we've been watching or learning about and just kind of seeing what the combination can do. So as you'll see, I'll mention, for example, Orsh's work quite a few times because I think it's really inspired by these kind of mode transformations he told us about earlier in the meeting, and then combining that with some other ideas due to, I'll mention like Fishman and White and Shook and Bauer also did on Gaussian Tensor Networks. So the basic idea is we want to see how to take this technology of Gaussian Tensor Networks and can we somehow apply it to interacting systems as well as not only just to non-interacting systems. So this is work that we're hoping to publish pretty soon. We're almost done with the draft. That's led by Ankun Wu, who's a very talented grad student over at Rutgers, just our neighboring institution to Flatiron Institute where I work. And together with Matt Fishman, who's the lead developer of the iTensor library and co-creator of the VUMPS algorithm and many other things, and also behind the main technology we'll be using in this work today. And then Jed Pixley, who's an expert on impurity model systems as well as many other things, who's Ankun's advisor. So the talk plan will just be to spend a little bit of time reviewing Gaussian tensor networks. They go by other names too, as the previous speaker mentioned, talking about match gate circuits. It's the same idea. I'm calling them Gaussian tensor networks. That's the idea that you can represent free fermion states in a very kind of controlled and accurate way as tensor networks, or find a mapping between them. And then the idea is to try to use these in the case of interacting systems to try to disentangle them and obtain some kind of benefits, both of speed and also maybe some insights too into the structure of the problem and the physics of the problem. So I'll just kind of do that review and then talk about the application specifically to impurity models, just as like a first stab at using this technology. So now, and by way of background, as a lot of you know, tensor networks were originally motivated by the problem of strong correlation. And so what's the strongly correlated problem? If you view it through the lens of either free fermion physics, or if you talk to a quantum chemist, they would say that strong correlation, and I think this is a perfectly good definition, is that your wave function is somehow the sum of like too many Slater determinants. It's not a single Slater determinant or not even two Slater determinants, but it might be some sum of where you need exponentially many Slater determinants in your sum in order to get good accuracy on your wave function. So that's a problem if you're using Slater determinant-based methods. So tensor networks were created, but they were created from a rather different point of view, starting over often some totally different picture of real space. And you can look at ideas like, say, projected entangled pair states, where you think about putting virtual degrees of freedom between things and then projecting them. It's like a very, very different starting point than a Slater determinant. So the point being that at the outset, there's not like a priori obvious connection or mapping between a Slater determinant and a tensor network. That took some time and some non-trivial steps to develop that link. Like, for example, you can actually do constructions that are fairly direct, like writing a Slater determinant as an MPS just by sort of using each setting of the bond dimension to represent a different free particle state, but you'll get a very suboptimal bond dimension, a very suboptimal rank if you do it that way. So these should be much more compressible, because we know things like the area law, that would hold for a free fermion state too. So how can you operationalize that to really get like an optimal tensor network? That's been figured out in the last few years, not by me. And so I'll just review that other work that I think is quite beautiful. And one of the ways of making this mapping is through quantum circuits. So how does that work? So the idea is, this is following this paper by Fishman and White that I'm citing down here, that's sort of the driving technology I'll be using, is that you start with some kind of generic non-interacting system. You can actually do this even for cases where you have like anomalous terms like C dagger terms as well. That generalization has recently been worked out in a paper by Dima Abanin. But here I'm just going to be talking about just this simpler case of kind of particle number conserving non-interacting system. You take your hopping terms, like your H, J, J prime here, and just do the usual thing that you all know. You diagonalize them to get what you could call orbitals, and then you can combine these orbitals together to get the correlation matrix, which is nothing just but C dagger I, Cj computed in the state that you want. Like, you could think of it as being the ground state, for example. So you just have that data, and now you have that correlation matrix. And then you use special properties of the correlation matrix. So the main property that you want to use, but then it's kind of like it's like a little refinement of that property, is that if you take the entire correlation matrix, which is what I'm drawing here as this entire matrix, both the red part and the gray part together, if you diagonalize the whole thing, then just because this is it came from a free fermion system, all the eigenvalues will be either exactly 0 or exactly 1. And it's just telling you, this orbital is occupied, this orbital is empty. That's the kind of usual property that it has. But that doesn't have like any locality to it at all. So that's just taking the whole system and saying, find some orbital, some single particle wave function that could cover the entire system if it wants to, that could be perfectly empty or perfectly occupied. So what you can do instead is you can make a trade-off. You can say, I'll give up a little bit of the occupancy having to be exactly 1 in order to localize one of those orbitals to be actually local now in space. So you could say, I really wish that orbital didn't cover the entire system, but just covered some little part of the system over here, like this that I'm calling a block, just this little beginning part. Can I still find one that has an occupancy that's almost 1 or almost 0? And you can. And that's not a generic statement, but that could come from the fact that you're working with some Hamiltonian that has some locality to it. Like maybe the terms are sort of short-ranged hopping and that kind of thing. So in many cases, not always, but in sort of many cases of interest, you can just take a block, like in the case of a 1D system, just take some block on the left and just keep growing the size of this block and take the corresponding part of the correlation matrix and just diagonalize that part. And you'll find very rapidly as you make it bigger and bigger that you'll sort of catch an eigenvalue that's almost 0 or 1, like very, very close, like close enough for what you need it for. And then you can find a few, maybe just 1 or 2 eigenvectors that have that property, and then by construction, they're completely localized inside that block. So here I'm showing doing that, and you can do that in a very nice way where you actually construct part of a circuit. Here, it's very important to understand that what I'm drawing on the right is not actually a quantum circuit, like living in a direct product space where this would be, say, a 2 to the 4 dimensional space. This is actually just a 4 by 4 matrix that I'm drawing over here. So this drawing is actually much more like when you see someone drawing a neural network and every line means just like a single number in a matrix. That's more like what this drawing means. So really it's like, you can think of this box here as just having like 2 numbers, or like 4 numbers in it, sorry, that would be access to those 4 different lines coming in. So these are just little matrices that I'm multiplying together, and the circuit is the idea that these are highly sparse matrices that you can multiply together. What they actually are is Givens rotations. So if you know how to do the QR decomposition by Givens rotations, where you're sort of zeroing out a row or a column, except maybe at the first element, that's what these blue boxes are. So this is, if you read this Fishman and White paper, they developed this this construction, but one like minor criticism of that paper is that I wish they had put like a symbol in the figure that says, this is not a tensor diagram, this is like a matrix diagram or something, or whatever those are called. You can lift them, exactly, so then you can lift it to a tensor diagram. But what's really important to understand is that it's kind of both things at once, like it lives in like 2 different worlds simultaneously, depending on how you interpret the drawing, if that's what you meant. Yeah, exactly. So I'll use that in just a second, actually. So then what you could say is that we're trying to kind of catch or localize what you could call inactive orbitals. And inactive in the sense that they're either filled or empty, so they're not really doing anything in the system. We just want to kind of project them out. So the intuition, again, is if you have, say, for example, it doesn't have to be, but in the easiest case, if you have a gapped state, then there's always a way to just choose this block large enough, like maybe 10 sites or 12 sites, and you'll find one of these inactive orbitals that you can localize. That's the idea. So here I'm just drawing a cartoon of one of these orbitals. Then once you've localized it, you do these rotations to come up with a new basis, where now in the new basis, the first site means that entire orbital. And then the second site through whatever, let's say the second through 10th site, is just whatever other kind of garbage is left when you do these rotations. Whatever these new indices mean, it doesn't really matter. It's just sort of the new basis. And then you just slide it over by 1, and then now you'll find some other orbital. I don't have a slide for this, but you'll have some other orbital that goes from here to here, including now another 1 or 2 sites over off in this region, and that'll get localized to be the second site, and the third site, and so on. So you're kind of finding this basis where all these inactive orbitals become your sites as you go. That's the idea. And when you iterate that procedure, so here's like finding the first inactive orbital, which now lives here, then you find the second inactive orbital, which now lives here, and the third and the fourth. You get an entire circuit depending on what pattern you do. Here now, as Yuto pointed out, this is now a circuit. So the drawing is the same, but now this is actually like a tensor network. It's actually a proper quantum circuit. And there's a very trivial mapping between these Givens rotations and these these match gate circuit elements. It's just, the parameters just kind of map over in a very straightforward way. It's the same parameters, but you just kind of know how to like lift them into a tensor diagram. And then you can interpret this construction as actually forming a matrix product state if you finally project these isolated orbitals, these inactive orbitals. You say, this is one that had nearly full occupancy, so I'll project it to the state where it's full. Then this one is nearly empty, so I'll just make it actually empty, and so on and so on. Each time you're making a tiny error, but you can control how much. When you're done, this is equivalent to a matrix product state, and the bond dimension is related to the block size through the fact that if you divide the first tensor here from the second one here, you're cutting 3 lines, dividing them. So you have this kind of upper bound on like what the bond dimension would be from that. You could call this whole construction a Gaussian tensor network. I just want to point out, although I'm not going to use it in these slides, there's also a mirror version in the same paper, which we're trying to see how to use as well in what we're doing. I'm not going to show results for that yet. But it's very interesting on a few levels because it's a really different way of making a mirror than I've seen in other papers. And I don't think I've seen too many applications of this outside that paper, but I just wanted to point it out. But it has advantages like that the orbitals you find actually really live in a finite region of the space, whereas in the MPS case, they can develop long tails that can go back all the way to the beginning of the system. Here, they really are kind of totally localized. So that's just a little detail about that paper I wanted to point out if you want to go read it. And then again, this point now I've made in words, but here's a slide about it, that once you have this circuit, it's 2 things at once. It's both a many-body quantum circuit, as shown in the diagram on the left, and at the same time, the parameters you computed are a single particle change of basis also. So for example, if you want to transform something like a C operator, like an annihilation operator, into your new basis, then it gives you a very efficient way, a very straightforward recipe of how to do that. Each of these boxes over here is a Givens rotation. It's just some matrix G that just has 4 non-zero numbers in it, like cosine, minus sine, and whatever. And then you just rotate the operator through all those Givens rotations, and you get the operator in the transform basis. So it's sort of straightforward to kind of bring over all your operators as well without having to do this expensive thing of actually applying a quantum circuit onto your operator or something that would be a lot less efficient. And so you could think about doing different things with this, this circuit. So again, the property that it's guaranteed to have is if you had computed the ground state just say using DMRG, not knowing it was a free fermion system or not caring about the free fermion structure, let's just say you had the ground state as an MPS, if you applied the circuit to it, it would approximately disentangle the state. So you'd end up with a product state where every other site would be filled or empty, just because that's how the circuit was constructed. So you could use it that way, like the point being, you can do quantum circuit things with it, but you could also do single particle things with it. So you could, as I mentioned, you can map operators. So you could take your original Hamiltonian now that was non-interacting, and then you could pass to this other basis where now I call the operators D in that basis for disentangled, and then apply those rotations onto your coefficients of your Hamiltonian and get some different ones. They might now be further neighbor, but actually they'll still be local. That's one nice thing about these constructions. Because it has this kind of MPS kind of structure to the circuit, it's not just gonna make now an arbitrary hopping that just crosses over your whole system. The hoppings will still decay and have kind of a locality to them just because of the way these circuits work. So that's all the background for that part. So we'll basically be interested in using that technology over on interacting systems. I just want to point out that a very closely related method was proposed, or a closely related set of ideas was proposed also by Shook and Bauer, though their construction is rather different in the technical details, which is nice. It kind of gives like a different route to obtaining some kind of similar results. So it also involves using the correlation matrix as kind of a central object, but it works really differently under the hood from my understanding, where it's more like a formalism for matrix product states where the virtual variables are fermionic degrees of freedom. But then they arrived at some kind of similar types of things where you have ways of mapping free fermion states to tensor networks, and you get really nice and very powerful algorithms. Like, for example, you get a non-interacting version of DMRG that's like way faster than regular DMRG would be, and you can do enormous systems very, very quickly. Like, here's some kind of huge, what is that, like 100,000 sites system that you can actually afford to compute very efficiently. So our idea was sort of to take this technology and just say, is that technology kind of trapped in the non-interacting world, and it's kind of a nice story over there, but it's just for non-interacting systems, or could this somehow be useful for interacting systems also? So then we were like, well, what would be the kind of interacting systems that this might be useful for? So in a very kind of cartoony intuition, we just said, well, maybe impurity models, because they're like mostly not interacting, right? I mean, I know that's just kind of a cartoon intuition, because of course, once something's interacting, I mean, it's interacting. But like the point being that, a more serious point being that if you actually thought of a very long lead going off to the right, let's say it was, 1 billion sites long, and then you started this process from the right of finding these orbitals from the right and kind of going over to the left, kind of how would the lead know that there's an interaction way over there if things are kind of local and you have an area law, and even if you had power law decaying correlations, you might have to go for a long while from the right until you actually realize there was an interaction over on the left. That was kind of the cartoon intuition. So let's consider systems like that, where you have an impurity site where there's an interaction, but it's totally local to that impurity site, and then you just have a large non-interacting bath or lead of just free fermions going over to the right. And then the idea will just be to ignore the interaction, so just set U to 0, no interaction, make this Gaussian circuit from the rest of the sites, or including the impurity site if you want, but just with the interaction turned off. Then take that same circuit, flip it around, and apply it onto the interacting system. So you could, for example, think about applying it onto the ground state of the interacting system and what would happen, basically. And to be concrete, let's just take the single impurity Anderson model. So you just have basically this bath with hopping T. You have some hybridization hopping V that's just hopping on and off of the impurity. You have some kind of energy shift here, and then very importantly, you have the interaction. Looks like the interaction of, say, the Hubbard model, but just on that one site. And then as a kind of purely technical detail, but it's important to understand some of the plots, we'll be solving it in the so-called, we call it split site form, where you basically say, well, the up and down electrons in the lead aren't really talking to each other. So that in the practice, that introduces a lot of extra entanglement that makes the calculation slow. So it's better just to split them apart and have spinless fermions, where there have two leads, and you have a lead on the left that just formally represents spin up electrons, and the one on the right formally represents spin down, but they're just treated as being just spinless fermions. And then we're gonna make the same gates one time, but then apply them from both ends going toward the middle. So this is just a little technical detail about how we actually did it. And then we're not gonna apply the gates to the impurity site, we'll just apply it to the leads only. And so how well does this all work? So, yeah. Oh, okay. Oh, really? Mm-hmm. Mm-hmm. You mean just the splitting part was not a good idea, you're saying? Mm-hmm. Yeah. Well, that's interesting. I mean, because it seemed to work okay for us. And the thing is, we actually just got the idea from some other people, like Lucas Cohn, for example, has a paper where they do that pretty recently, where they're doing things like developing finite temperature methods for impurity models and some other work like that. So, mm-hmm. 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 Okay, but you're basically saying that it didn't work too well to split it this way. But by the way, the splitting thing is really more of a pure detail of what we're doing. It's just, yeah. Mm-hmm. Mm. Oh, okay. Mm. Mm. Yeah, here I'd say we're more interested in this as just a laboratory, as like a proof of concept thing. We're not sort of trying to go for state-of-the-art impurity physics in this work so much. We're more just kind of like wanting kind of like, let's just get the energy correct to a couple of digits sort of level of, that kind of thing. And really we're intending this more broadly not to be just a technique for impurity models. Yeah, yeah. Mm-hmm. Mm. Mm. Oh, okay. Mm-hmm. Oh, so you're saying there's some cases where one's better, some where the other's better? Hmm. Great. That's a really interesting comment, because one thing that I'm not going to show, but we're working on a little bit, is after we do these transformations, doing what you said about looking at mutual information to maybe kind of reorganize the ordering again. Because once you go to this other basis that's on top of this figure here, it's less clear sort of what order they should be in 1D, and there could be maybe a better order, actually, especially when you do the Mira version. Mm-hmm. Oh, yeah. Uh-huh. Mm-hmm. Okay, great. But yeah, here just to emphasize, this was more of just also for us, it was just a technical thing, because we had this free fermion technology was only coded for spinless fermions too. That was part of it as well. So we thought it was a nice little 2-for-1 combo for us. But so basically, again, we have this kind of, you can think of it as just two impurity models that are sort of back to back if you want, or a model with an impurity in the middle of it. And we're going to do this transformation. And so again, our goal now is, remember now we're putting an interacting system underneath, but we're taking these gates that were purely designed for a non-interacting system. That's the idea. So I mean, Ors won't be surprised about what result is, but we were kind of surprised. It was inspired by the stuff he was doing. So how well does this work? So here's us starting to apply. Let's just say we only apply a few of the gates, over here, and now we're kind of going back across. So we apply a few, and then we can see the entanglement now is going to 0, where we've applied the gate so far. And then we apply some more, and the entanglement's going to 0, going to 0. So we're just basically shooting the entanglement almost to 0, except where we haven't applied the gates. And finally, we apply them almost across the whole system. And there's some kind of artifact over here where we've left the impurity sites untouched over on the left. But then the rest of the system, the entanglement has been drastically decreased, almost to 0. Not quite, but very, very low. And then you can look at what's the bond dimension of the ground state in this new basis, and it's almost 1 everywhere, way out here. And then finally, there's just a little bit of growth of the bond dimension near the impurity. If you actually lower that's using like a moderate cutoff in DMRG. If you lower the cutoff, the bond dimension will come up, like maybe out here in the tail, it'll come up to be 10 or 20 or something like that, because you're kind of catching these little errors that you made in the transformation. But that's still not very big. But if you use a moderate cutoff, this is what you get. And that's for the case of u equals 1. You can do it again also for a larger u. We've also tried u equals 100, and it works as well. So, and this is for now an interacting system. So we thought that was kind of neat that this happens. So, exactly right, yeah. And what's really kind of fun about this case is, in this case, we didn't, but we could have changed V, which is that hopping on and off the impurity, but we just left it the same in both cases, and we only changed U. So it's actually the same gates in both cases, independent of U, which is kind of fun too. So, but of course, a more natural thing to do would be to, like, if V changed, make different gates involving V. Also, a very obvious idea would be to try to do a mean field calculation, do like a Hartree-Fock calculation and use that. Maybe that does even better. We haven't tried that yet, but it's something on our list to try. That's a good question. Yeah, we kind of do check. Depends on which aspect of it you're talking about, but I'll have a plot where we show like a universal collapse of a certain length scale that we see. It's going to come. Yeah, there's a certain length scale associated with the entanglement going down, and we catch that, and it still has the right like universal shape. Actually, I'll show it in a second. So the cartoon that we have in our head is that it's like the entanglement sort of was divided into two pieces. There's this like massive free fermion part that's taking up a bunch of computer time, and then the other part that's like coming from the interaction, and it's like we're able to just subtract the free fermion part off ahead of time by doing everything at the level of a single particle calculation. So then, let's see if I put that here. Forget if I have a slide coming up with that, or yeah. Yes. I like that question. Yeah, that's a great question. So what if we went to the eigenbasis of the chain, like say of the non-interacting system? Right, exactly. So I think this is a potentially really important point. We've only looked at it in this one case of a pretty easy model to solve that probably would work. A lot of different methods could solve really well. But we believe this is a really key difference, that that idea has been thought about a little while, the idea that like, let's go to momentum space, say, if you did the case of like a translation invariant system. And then, we know the ground state is a product state there. But as soon as you add an interaction, the interaction is going to be very like non-local in that basis. And a lot of the things that make tensor networks succeed aren't going to hold anymore. So here, this Fishman-White algorithm is making a little trade-off. It's saying, I'll trade off a little bit of not really being all the way into the energy eigenbasis for locality. So it's more like using wavelets versus using the Fourier transform. So sort of the same trade-off that wavelets make. I think it's, I don't know if you can totally argue that it's optimal, but it's like sort of has optimal scaling, let's say. So it sort of has the right scaling that the optimal thing would have. And like again, it might be kind of similar to if you know about wavelets, how there might be like one family of wavelets that's like really optimal for some task that you're doing, and then another family that's a little suboptimal but still has all the right key scaling properties and the properties that you want, like orthogonality, and sort of optimal in that sense, I would say, near optimal. So I think that's the key point, is that you're going from local Hamiltonian to local Hamiltonian. So you still can use tensor networks even with interactions and still have all those guarantees about area law and everything like that, while getting the benefits of being in something like the free fermion eigenbasis at the same time. So you're trying to kind of balance those two considerations. So I wanted to point out that we didn't think of most of this really. So Fishman and White did that first part. This whole idea also of transforming the basis and seeing that helps you with fermions is something that these authors, Krumno, Eisert, and Legeza, have explored quite extensively. So they've already shown that this idea has merit and can really help a lot of problems. So you can use it to do solving quantum chemistry problems. You can apply it even in 2D, even in the case of doing time evolution. So they have works on all those things and even more than I show here. And their approach is to find these gates by minimizing the entanglement entropy. So you basically are saying what's on a certain step of a calculation, like say a DMRG calculation, what's the best rotation I could do of the basis that will, say, minimize a certain kind of entanglement entropy, like a certain Rényi entropy, for example. So then if they've already been doing that, why do we need to do it the way we did? I would argue that our approach is sort of taking theirs, but kind of just tweaking it a little bit, using this other technology, this Gaussian Tensor technology, but then there could be a lot of benefits to doing it that way, the way we're doing it. So one benefit is that we don't need to do this optimization during the calculation. We just do this calculation up front, and that calculation is all happening at a single particle level. So there's no many-body calculations involved in getting the gates. You just get them from purely free fermion calculations. Also, you get a theory of where the gates are coming from. So you get more of a picture of like, rather than the gates coming from at the end of an optimization process, you have more of an understanding of like, these gates are because you're connected to a free fermion limit that's an MPS, it has more of like a story. Very importantly, it's also, you can stay in the single particle space, so you can apply those gates to your Hamiltonian at the operator level. And most crucially, they preserve locality of the Hamiltonian. So you're not going to produce very non-local operators. Like for example, if you have like a density-density interaction in your Hamiltonian originally, you're not, in the approach we're taking, going to produce an arbitrary 4 fermion term. You might have some 4 fermion terms, but they're going to be still local, like only in a certain patch in space. You're not going to just have this tensor with non-zero entries kind of going all over your system globally. So yeah, I think that'd be a great idea, yeah. Exactly. Or just using this way to initialize the other way, for example. Yeah. Yeah, because maybe in the end it's still better to do like what you're doing, but to do it later in the calculation or something like that. Or, yeah, I think that'd be great. Yeah, exactly. So yeah, exactly. So I think there's definitely a lot more to be tried. Well, it's true, there is an approximation here, but we use it only as a change of basis, though. So we aren't, in the end, throwing away anything, so. Well, yeah, actually, I should say, really, there's no approximation. Sorry, it's approximate in the sense that it's not finding the absolute perfect free fermion state, but you only really pay that approximation if you project, like I showed earlier on, to say, okay, now I take this to be the state. But if you're not trying to make the state, if you're just trying to use it as a circuit, as a change of basis, then as you said, there's really no approximation. It's just a different basis. And then really the DMRG calculation at the end will clean up any leftover errors that you might have made or something, basically. So let me just, for the sake of time, kind of go through the rest. I just wanted to point out some other recent related works, or one recent, one not so recent. So this really fascinated me to see. There was a recent work by this group of authors that was coming up with essentially the same idea, but just taking it in a very different direction. So their idea was to take precisely the same circuit, like you can see that drawing looks just like the one I had earlier, precisely the same circuit, also from the Fishman and White paper, but then to use this as an ansatz for quantum computing and to say, what if we were interested in preparing fermionic states for a quantum computer, but we wanted to somehow remove a lot of the work up front through a classical calculation. So you could say, well, let's just figure that a lot of the gates will be close to or be exactly this Gaussian tensor network. Then we'll just kind of supplement these gates with some extra part that will handle the interactions. And they found that worked very well for what they wanted to do. So in the end, it's probably the same thing that we're finding. We're just doing it in reverse. We're basically saying, let's not, we're reverse in a few different ways, but we're saying let's not so much use this as an ansatz, but let's use this as a basis transformation, and then we'll let our numerical method find this part, rather than us supplying that part as something that we would, say, do gradient descent on, or something like that. Also, we're trying to do it all in the classical computing side of things. Another work this reminded me of is actually from 2012. This was Frank Paulman and collaborators exploring the idea that wave functions of weakly correlated systems may have different parts, like maybe it's mostly a Slater determinant supplemented with something else. So there though, it's interesting because they tried something that's kind of like the reverse of what we're doing. It's like instead of the free fermion part being the part that's connected to the sites, then putting the interactions on top, it's kind of the other way around. It's like the free fermion is the part that's the deepest inside, and then you put the corrections kind of on top in the form of an MPO. So I don't know the precise connection of that idea to what we're doing, but it's just pointing out that this notion that weakly correlated states might sort of have two different pieces that kind of interact with each other is just kind of been out there for a while. So we're just sort of taking it in a different direction. So then just in terms of what can we do with this besides just getting the ground state, or just taking the ground state and transforming it? Well, one point that may have already been obvious to a lot of you is that when I showed the result earlier, I kind of talked as if we're taking the ground state first, then applying the circuit to it. But what we can actually do is apply the circuit to the Hamiltonian first before you ever do a many-body calculation. And then you've never actually touched any kind of highly entangled state the whole time. You're just doing free fermion thing, very quick Hamiltonian transformation. Then you work entirely in the transform basis. But it's actually not obvious that that's a good idea. It may not pay off because you're going to end up with a Hamiltonian that's much more complicated and further ranged. What if all the cost just moves there into making the Hamiltonian, and then you just have say if you use an MPO, what if your MPO just blows up? And then the calculation's going to be just as slow, if not slower. That could happen, right? But it turns out that doesn't happen in the cases we've looked at just in 1D. We actually tried something that we thought would help, which would be to cut off the longer range toppings after a certain size. Like once they got below a size, just cut them off. But that actually led to a larger bond dimension of the MPO, which in hindsight is probably because it's like there's a step in the hoppings. So if you let the hoppings just all go in, I think what happens is that now they have a smooth tail, and that can be compressed better. So we're using compression techniques to make the MPO. And we find that the bond dimension just plateaus as we do bigger and bigger systems to something like 20 for the cases I was showing. If you actually, it works better and better if you just put all the terms in, basically. Totally agree, yeah. Okay, that's a good point. Yeah, I'm glad it's not the reverse, right? Yeah, otherwise it might rule this out as a method for this kind of physics, totally. So it's really good that actually putting everything in is really the best strategy. So great, so we get an MPO that's not too bad, just grows from being bond dimension, 4 to bond dimension 20 when we go to the other basis. But then as I showed before, the MPS that you get, it turns out to be much smaller, like bond dimension can be, 1 out in the tail and maybe grows to 10 or 20 near the impurity or something. In some cases, it grows more to 70, but that's still much, much less than it was originally. Then when you finally put it all together, the net thing is that you get a very fast DMRG calculation just for the ground state. So here's showing the speed up of just dividing, the speed, the original by the new one, and you can see that it just actually keeps growing. You just get, 10 times faster calculations, say. So that's really nice. One other thing that we're exploring, right now we're doing it in kind of just a cheating way, but we're working on like a nicer way, which is getting properties by going through that procedure where we map the Hamiltonian and get the ground state, then get properties there and compare them to what if we had worked in the original basis. Of course, and these are not super hard calculations, so you can run them both to very high accuracy if you want. But if you work at kind of like a fixed effort, roughly, and compare the results you get, we're finding that going through this mapping and then coming back is giving better results right away. Whereas if we win in the original basis, we have to work harder and harder and harder to get similar quality results. So here what we do is we calculate in the map basis, then we transform back as a mini-body circuit, then we calculate properties. But what we should do really is actually map some operators over too and just measure everything in the mapped basis. So then lastly, can we see some physics? This is kind of getting to your question, Andreas. So can we see some physics this way too? Like, what is there some kind of meaning to this, like, interacting part of the entanglement, so to speak? One idea is we could look at where that impurity entanglement or interacting entanglement, if you want, where that goes to 0 and see if that gives us a physical length scale in the problem in some way. And one way to find this physical length scale, there's a nice paper by one of our co-authors, Jed Pixley, and his collaborators in this PRL, is they had that idea already. They said, what if we take one of these impurity models and we compute what would the entanglement be if we just had the lead, and then you subtract that off and look at the result, and then do some kind of scaling and try to find like a universal collapse. So they already had that idea in that paper, which is why we wanted to try it too. So we could do their procedure as like a baseline, or we could do this Gaussian tensor network transformation and try to get the same collapse that way. And this is showing the results. So that's if we repeat the procedure from that PRL, where you basically subtract off the non-interacting part of the entanglement, look at the rest, and then determine a length scale of when does that entanglement go to 0, like what distance does that happen? And then you use that to rescale the x-axis, and you do this for different sizes of interaction. You find they all collapse on top of each other, these entanglement curves. We did the same thing, but we didn't do any subtraction. We just transformed to the new basis. The entanglement just already looks like this. It just has this shape. And then we just figure out where does it go to 0, use that to determine this length scale CK, and then transform the basis, transform the x-axis that way, and we get this universal collapse also. So, yeah, that's right. J is the condo. J, it's just here. We're just determining it from like v squared over u times, I think, 4 or something. Yeah, 5 minutes. Thanks. Okay. That may be. So that's good feedback. Yeah, we can try to explore some even smaller ones. Yeah. Okay. Good to know. Yeah, I'm not sort of a total impurity model like person, so this is a good feedback. This is some of the feedback I actually wanted to get from this audience. So, yeah, but we've tried a very wide range of interaction strengths, and it's all working well. Like even if we crank U up to like 100 or other things like that. So. Okay. Okay, then we'll have to watch that carefully and like make sure we scale the system size up too. Yeah, we're not so much going for like ultra high precision condo physics in what we're doing here, but but you're right. That's kind of a question. Like if our statement is people who should use this, we'd have to then be really careful about those things. Yeah. Yeah, but that makes sense. Yeah. Yeah, or I meant very like say low energy physics or something. Yeah, that's true. We would have to be extra careful in that case. But so that would be a good thing for us to be sure that we like cover that limit. I agree. So that's a good point. Okay, so one last little idea that we're just kind of beginning to explore. So this part's all non-interacting so far. We haven't done it with interactions, but could we do this to disentangle dynamics? So I mean, some of this previous work I mentioned by Orsh has already explored that. So we think this should work. We're just sort of at the beginning of trying it out. But what if we use these same disentangling gates, but we evolve the system in time? The way we're making the time evolution non-trivial is we're quenching the V. So we're just keeping U to be 0. So it's all non-interacting, and then just change the V, like this hybridization V at the beginning of the time evolution. And then what that does is in the original basis, as you go to different times, there's like a ripple in the entanglement. So this is showing the entanglement entropy. At first, it just has this kind of rainbow shape. That's the blue curve. Then there's like a ripple that propagates outward. So here's at time 10, and then at time 20, time 40. Then we do the whole thing again in this disentangled basis, and we see at first there's no entanglement, which that there should be by construction, no entanglement. Then at a short time there's some, but it's sort of all, to the left, and it's corresponding to the location of this ripple in the original basis. And then it grows and grows, and again this distance is kind of again corresponding to this feature. So we see that the whole time the entanglement in this transform basis is still less than in the original basis. So that's kind of encouraging. So we want to know now, can we try this on an interacting system? There may just be some purely technical challenges to do that, which is that if you're using, like, we're going to use TDVP, it's very sensitive to, like, if you have a very good basis or not. Whereas this method is taking you all the way to a product state basis. So we'll probably have to be careful about using this kind of different basis expansion methods to make sure this all really works and everything. So our initial attempts, it didn't go so great. We think just for purely those technical reasons where the basis is very poor and you have to be very careful to grow it properly. But if we can get all that to work well, and those technologies are improving, then we think maybe this could be a productive combination of things to do. I think all the kind of future directions are fairly obvious, but one of them is just, is it worthwhile to dig in more about what the success of this idea says about some kind of generic structure of interacting states? Like, is it really fruitful to think of them as that you have some kind of, most of the entanglement is coming from some non-interacting part, and you just have this small part on top that's just some correction. I'm kind of drawing it this way also for a second reason, which is when there's actually some really nice works, like for example by Evenbly and Vidal, that actually talks about what the structure of systems that are like impurity models might be like, where you think about two mirrors for the two leads that are first disconnected, and then if you brought them together and then changed the Hamiltonian locally, how you could think of this as an effective Wilson chain going on top of the mirror. So they already kind of had that idea, but it hasn't been really tested out, I would say, all the way numerically, like sort of operationalizing it as a practical tool for calculations. So can some of those insights really be kind of operationalized for calculations and used to gain some advantage numerically? And then, of course, just how general purpose is this? Like, how well will this work if you go to systems with interactions everywhere, not just impurity models? How about going beyond 1D? A key one in my mind, too, is can you push this? How far can you push this beyond just kind of local Hamiltonians? Like, let's say you took a really messy impurity model that came like in a DMFT calculation or something that's kind of a lot more complicated. Can this technology help you, or does that original transformation really only work if things are kind of rather nice and local at the beginning? Also, can we use better non-interacting states, like doing some kind of self-consistent calculation or Hartree-Fock at the beginning, or something maybe even better where we use the interacting calculation back again to get better gates? But then we're getting quite close to what you guys are doing already. So it's probably good at that point to sort of marry those techniques together. So I'd appreciate any feedback you have about, like, is this the only example where it's going to work, or do you think this will keep working on a lot of other cases? What would be some interesting applications to try? So thanks a lot. Yeah. Mm-hmm.